Welcome back to the lectures. Once we are almost end our second week, almost end the last part 1 lecture for the second week, and you must be getting pretty bored and upset by that I am always writing mean variance portfolio optimization. Please understand that there are two important aspects of the financial profession, the finance profession. One important aspect is to manage risk, which could be your own investment or which could be of others' investment. So, basically we have two parts: management of risk plus pricing financial instruments. We are essentially now studying the management of risk. I am sure that many of among you, at least some of you who are listening to these lectures, would one day become risk managers in reputed financial firms, where you have to essentially manage other people's risk, your customers' risk as he invests in the market. You have to develop a portfolio for him or her. So, one important aspect of risk management is a mean variance portfolio optimization. It is not that it is the only way by which this mean variance stuff is done. It can also be done by using other measures of risk, for example, the value at risk or conditional value at risk and so on and so forth. But the mean variance approach due to Markovitch remains a very fundamental one. We have discussed a lot about how to handle that, what is it, and how to compute, even under certain natural assumptions, how to compute the weights, in fact unique weights. So, you can uniquely define your portfolio. That is what we had discussed in the last class. But what I intend to do now here, as I have promised you, to show how reward and risk interacts, means how does the return and the risks interact between them. So, here I will largely discuss from chapter 2 of this book called Introduction to Mathematical Finance Forms by Stephen Romans. So, I will just discuss this from this book, where it has been beautifully described, and this risk has been, the risk versus reward or risk versus rate of return has been described in terms of only two assets, that is, you are investing in two of the assets, the market containing just two assets. It is a very simplified model, but gives you somewhat an understanding of how things might just work. So, here I will have two assets, assets A1 and asset A2. So, these are my assets. So, on which this is a two asset market, stocks of certain companies, and I have an expected return mu1 here, return, and the risk, which is the variance, similarly mu2 here, and the risk is. So, if you have a portfolio consisting of these two things, then that portfolio would essentially consist of, so the portfolio essentially consisting of these two things, and the expected return of the portfolio is T plus mu1 and 1 minus T plus mu2, where T is the amount of weight I have given to the first asset, 1 minus T is the amount of weight I have associated with the second asset. Okay. So, their variance is So, the variance is this one, rho 1 2 is rho 1 2 is the correlation coefficient between 1 and 2. So, correlation coefficient actually means the covariance 1 2 divided by sigma 1 sigma 2. That is the meaning of correlation coefficient. And this correlation coefficient, of course, you can understand has to be between 1 and -1. Now, you have this scenario, okay. So, this is what you have. Now, assume for the sake of brevity that is 0 bigger than sigma 1. So, everything has a positive risk, but equal to sigma 2 possibly. So, this is a assumption. So, we will work under that particular assumption. So, you know how to calculate the mean of the portfolio and the variance of the portfolio, which we have already done earlier. So, here it is just I am writing it down, because you will immediately understand. Now, suppose first case 1, in case 1, let us assume that this is uncorrelated, that these two events are uncorrelated, that is these two assets have no correlation between them. So, I assume that rho 1 2 okay. Once I do that, my sigma square becomes t square sigma 1 square 1 minus t square sigma 2 square plus 2t into 1 minus t sigma 1 sigma 2. So, once you have done that, you can rearrange these and put it in this form. So, this is what I have after simplification. Okay. So, you know that sigma 1 is strictly bigger than 0 and sigma 2 is either equal or strictly bigger than sigma 1. So, sigma 1 square plus sigma 2 square that comes here is non-negative, and thus it is truly a quadratic function rather than an affine function. Okay. So, this is something you have to keep in mind. So, basically now what I have represented, I represented the variance or the risk in terms of the weights, and these sigma 1 sigma 2 are fixed numbers known earlier about these assets. Okay. Now, before I move on to do something, let me see for what value of t, t is playing the role of the weight here, W1 and W2 is 1 minus t. So, let me see for what value of t does this sigma square achieves the minimum, and that is exactly what we want to know. Then by simple differentiation, or standard one, Tm sigma 2 square so the minimum value of t, the value of t which minimizes sigma square is this. So, this is the weight I have to provide to each of the, and you observe that this is strictly bigger than 0. this is the weight that I have to so this is the weight I have to actually set to the first element, and 1 minus Tm is the weight I have sent to the second element. Okay, so that's something crucial, and the variance here so the variance here is as follows. Now we will come to two cases. So this is the value of the weight that I have to attach to the first element, and hence 1 minus Tm to the second element, which is strictly bigger than 0. And for that the allowed risk is this. So, the minimum value of the risk is this. So, see how it is linked with whatever variance we have for the 2 asset problem. Now, this is the minimum weight that you required, 1 minus Tm is also positive, right. So, so, this is what we will have with the counterpart of the weight. So, this is W1, this is W2, right. Now, what we do once we know this, we will talk about what happens if I take rho 1 to be perfectly, that is 1 and 2 are perfectly correlated. So, rho 1 2 is live between 1 and minus 1. When it is perfectly correlated, rho 1 2 is 0. When it is not correlated, then when it is perfectly correlated, rho 1 2 is 1, and when it is not perfectly, what to say, correlated, then we can say rho 1 2 is minus 1, or you can have rho 1 2 to be 0. So, what it shows here? It shows that if rho 1 2 is 0, what we get? We get this non-negative weights and the risk which depends on sigma 1 square, sigma 2 square, sigma 1 square plus sigma 2 square, which is constant. So, what it shows here is the following, that even if you have no correlation, you can find weights which sum up to 1, but the sigma m square is of a certain amount. Okay. So, we have just written down quite hurriedly, okay, if there is no correlation, then what is the weight which would minimize the variance, and then we have written down what would be the variance under that minimum weight. And we said that, okay, the minimum variance would be something quite significant, the variance does not go down even if the things are uncorrelated, but the total variance can be made lesser than the minimum of the 2 variances, and you do not have any short selling to do. Now, how am I reaching and how am I getting these Tm values? So, here I am considering 2 cases. So, one was 0 when there was no correlation. So, one is when the correlation is perfect, that is called perfect correlation, when rho 1 2 is 1, and it is completely negative correlation, that is rho 1 2 is minus 1. So, if something increases, something decreases, right? So, that sort of thing. So, it is completely opposite. So, what I do here is, here I put rho 1 2 is 1 in the expression of sigma square, then I make a simplification. and then I take the derivative, equate it to 0, and then I say, okay, whatever you get, whatever t solves makes the derivative 0 is the answer. Of course, I want to have sigma 2 not equal to sigma 1, because if I have sigma 2 equal to sigma 1, then sigma square is equal to sigma 2 square, there is nothing to say. Now, here you may ask me that how do you know that this is truly the minimizer, which you could ask me even in the case in the row 1 to a 0. The answer comes from the fact that this is actually a convex function. In fact, any variance is a convex function. So, when you have a convex function, for example, we have defined a convex function, we will again define a convex function. A convex function is of this form. Okay. So, again let me recall that, for example, if you take an example like this, if x is half x ax, once a is positive semi-definite, which I am writing in short as PSD, then f is convex. Then f is convex. Now, for here, so the variance that we have is always convex, the variance is written as W sigma W. Now, for a convex function, we said it is very important to know that when you have when you want to minimize a convex function even over a convex set, every local minimum is global. There is nothing called a local minimum as such. Now, the interesting part is this is a differentiable convex function. So, are we trying to say that every critical point, means any point which satisfies the derivative equal to 0 is also a minimizer of a global minimizer of a convex function? The answer is yes, because if you look at the diagram of a convex function, a graph is something like this, and so if you take a tangent at any point, the tangent, if the function is differentiable, you will have a unique tangent at every point, and the tangent is lying below the graph. This fact in higher dimension is expressed by the fact that a function is convex if and only if the following result holds true. So, f is convex if and only if this thing happens. Now, if x star is a point where grad f x is 0, now if grad f of x star is 0, and from here, and f is known to be convex because this function is convex, then fy minus f of x star is grad of f of x star y minus x star for all y. So, if I fix my x, this will happen with all y, because this is true for all x y. So, what does it mean? Because this is 0, so this thing becomes 0. So, that will immediately tell me that fy is greater than or equal to fx star for all y, showing that x star is the minimizer. So, any critical point, that is a point at which the gradient is 0, is a minimizer. So, here we have a equation in one variable, so we take the derivative. So, once we know that the derivative is 0, you know that this is a minimizer. But in this particular case, when there is a perfect correlation, this is something pretty amazing. Amazing part is the following, that if you have Tm, one of the weights which is strictly bigger than 0, the other weight would be negative. So, which means if you want to invest in the first one, A1, if you want to invest in the first instrument, you actually cannot invest in the second instrument, but rather short sell it. You have to get it from someone and sell it in the market. So, here we have to do short selling. And let us see what is the case of sigma now, value of sigma square. So, sigma square is sigma 1 minus sigma 2, sigma 2, sorry, this is sigma 2 sigma 2 minus sigma 1 plus sigma 1. So, this will cancel out to minus 1, sorry sigma 2, this will cancel out to be minus sigma 2, and so this is 0. So, if you have a perfect correlation, then you have to short sell, but your risk would be 0. So, let us come to the case when you do not have perfect correlation, they are negatively correlated, they are essentially behaving in opposite fashion. Then you have rho 1 2 equal to minus 1, and now so rho 1 2 is equal to minus 1, and then you again do the same thing, you write the sigma square which is now of this form, take the derivative and put it equal to 0 and take Tm. So, here Tm is positive, 1 minus Tm is positive, so no short selling is required. So, now I want to find the sigma square. What is the sigma square when I got the optimal weights? The sigma square is sigma 1 plus sigma 2, and here I have sigma 2 by sigma 1 plus sigma 2 minus sigma 2, which is 0. So, again the variance becomes 0. So, when you have positive correlation, even if you have to short sell, you have 0 risk. When you have negative correlation where you do not have to short sell, you can simply invest and there is no risk, you will get your expected return possibly. So, this is an idealistic situation which cannot happen. So, your rho has to be somewhere, 0 is acceptable, but rho has to be strictly somewhere between minus 1 and plus 1. So, this is a very nice way of, it is very difficult to get situations where you have, even if you have two things where rho 1 2 would be equal to minus 1. So, it allows us to conclude, at least from this example, that the rho usually between two objects, so rho 1 2, say 2 assets, should always be between minus 1 and plus 1. Now, can this idea tell us something more? In the finance world, for example, people do not really go about in this way relating sigma in terms of the weights and then trying to analyze that. They do it in some called the variance mean diagram or the standard deviation mean diagram, and that is exactly what we are now going to study. Now, what we are going to discuss is a mean variance diagram. It is very funny that the mean or expected mean R bar, which we will write as mu for, because we is only two things, two asset portfolio and sigma, and people want to discuss the interaction between sigma and R bar, that is called the mean. So, you can have various portfolios with various means and variances, right. So, this is called the mean standard deviation diagram, mean standard deviation diagram. Okay. So, now what is interesting to me for the moment is the following. Again, let us have two assets and let us have mu 1 and mu 2 be their expected returns, and so portfolio expected return is this, and the variance is omega 1 square sigma 1 square omega 2 square, sorry, W2 square sigma 2 square plus 2 rho 1 2 W1 W2 sigma 1 2 sigma 1 sigma 2, sorry. So, or rather I should write it in this way, oh, chalk. Okay, so I should write it as plus 2 W1 W2 rho into sigma 1 sigma 2, rho 1 2. So, this whole thing is nothing but the covariance between 1 and 2. Now, what I am going to do, again I will consider this is just for simplicity, and in fact when I will draw the diagrams I will possibly take mu 2 bigger than mu 1, that will make it easy for us to understand. So, here of course I should have the weights, the normalized weights W1 plus W2 equal to 1. So, that is the standard thing. So, now once I put W1 plus W2 equal to 1, I can further rewrite, So, we will divide the whole thing into couple of things. So, we will first look into the case rho is plus minus 1, and then of course, we will look into the case rho is between minus 1 and plus 1, rho sorry not rho 1 2. Now, this is my standard thing. Now, we will try to put W1 as S and W2 as 1 minus S. For our simplicity, we will do that. But first, let us, so we can write everything in terms of S. So, basically then mu and sigma square instead of writing a function relation between mu and sigma square, we will make a parametric representation of mu sigma square. So, and then we can draw the locus of points which passes through the points mu sigma square connected by the parametric relationship. So, this is basic coordinate geometry. So, let us consider the first case where rho 1 2 is equal to plus minus 1. If you do that, then you can immediately write sigma square, here they do not write in terms of sigma square, but sigma. So, instead of r bar, let me just put mu, sigma mu diagram, mean standard deviation diagram. So, sigma can now be written as square. So, you get the mod of this, and then essentially you are talking about plus and minus depending on whether rho 1 2 is plus 1 or minus 1. So, the parametric equations, so this is like, for example, if you take a parabola y square equal to 4ax, then you have x equal to at and y equal to at square, that is the type of parameterization that you do basically. So, when you have for example, if you write if you have a circle, so if you can write x is equal to r cos theta and y equal to r sin theta, then of course x square plus y square is equal to r square. So, this is a parametric representation in terms of the circle. So, here instead of speaking of just x and y, you are looking at everything in terms of theta. Now, so you write the parametric equation as sigma, sorry, maybe I should start with mu. Mu is nothing but the same thing, but you write S mu 1 plus 1 minus S mu 2, and then you write sigma in this particular case as S plus 1 minus S sigma 2. So, here again we have that perfectly correlated and bad correlated space. Now, instead of this, how would I write this diagram? How will I draw this diagram? So, this is our next step. So, how will I draw this diagram? So, drawing this diagram is very, very important. So, instead of taking the step today in this class or this particular class to draw the diagram, I leave it to you to ponder over it how to draw the diagram. So, in tomorrow's class we will start with discussing about drawing the diagram. right. So, once we know how to draw the diagram, things would be much more simpler. Once we do that, we will talk about what would happen in the case of rho is between -1 and +1, and that would give you a fairly good idea about how the reward and risk is actually interacting. Thank you. I will see you in the next class.